So hello everyone, my name is Sepúlveda and I'm a professor at the Faculty of Mathematics and Information Science from the Warsaw University of Technology. I'm also a collaborator of the Center of Statistics and Application of University of Lisbon. Today I'm going to talk about the 3 sigma rule, and I would like to address the question, is this rule a beauty or a beast in serology data analysis? Before I start, I would like to acknowledge that the title is not totally rigorous. Actually, I would like just to emphasize that I'm going to talk about the one-sided 3 sigma rule and not the two-sided 3 sigma rule. So what is serology data? So serology data is actually data from antibody concentrations and calculated in the different individuals, okay? And because you're dealing with antibody concentrations, your data is actually quantitative. As I can show you here in this histogram of antibody distribution related to the IgM antibodies against the S1 glycoprotein from the SARS-CoV-2. So antibodies are produced every time that you encounter an infection agent, and so serology data analysis is very important to understand how what kind of immune response people have when they encounter a certain infection. So what's the basic problem in serology data analysis? And I call this problem the problem of mixed populations. So in your histogram that shown before, actually you have a mixed population. And what do I mean by this mixed population is actually you have some individuals that actually have actually antibodies, and then you have other individuals that actually have don't have any antibodies, or they have antibodies that are so low that I can consider that they don't have any antibodies. So in a way, what we would like to understand is to identify these two classes of individuals. So the interpretation, just to be much more clear about this, is that you have some individuals whose antibody concentrations are actually at the level of the background noise of the lab experiment. So if that's the case, in these individuals will be considered seronegative, and what it means is that they don't have antibodies that you're interested in. Then you have other individuals that actually the antibody concentrations are high enough from the background noise, so they will actually provide you a biological signal related to the presence of antibodies. So these individuals will be called seropositive. So to divide the individual or the population in these seronegative and seropositive individuals, you can use a very simple approach. So you can just go to this histogram and just put one cutoff at some point. So in the individuals whose antibody concentrations are actually below this cutoff will be considered seronegative, and individuals whose antibody concentration are above that threshold, they're going to be considered seropositive. And as you can see, this is not a perfect classification. So the fundamental question related to this talk is actually about this cutoff, and that's when it comes the 3 sigma rule. So what it means is that this cutoff you're going to determine by the mean of the seronegative population plus 3 times the standard deviation of that seronegative population. Okay. This actually, the idea comes from from a normal distribution, where actually this mean plus 3 times the standard deviation provides you a very high percentile, so it's around 99.9. Okay, and the normal distribution, when actually you change the variation of the distribution, actually the percentile doesn't change. So that's something good. So you have 2 properties. One is actually very high percentile, and this actually percentile doesn't change with the variance of the normal distribution. The problem comes when actually you have skew distributions and then in that case you're going to have the 3 sigma rule. When actually you calculate the cutoff, the percentile can actually be much lower than the normal, the one then associated with the normal distribution. So in practice, you don't know what's happening in the seronegative population, so you have to estimate the mean and the standard deviation of this population. And for that, you have 2 approaches. One of them is actually you use data from a known seronegative population, and then you apply this one-sided 3 sigma rule. The second approach is actually you analyze the data from the field, but now you use a 2-component mixture model. So in that case, what you're going to assume is that you have the data is a mixture of 2 components. One actually is coming the seronegative population, and another one is from the seropositive population. And then after estimating these components, then you apply the one-sided 3-gun rule using the estimates provided to the seronegative population. Today I'm just going to focus on the first case, so how to estimate the seropositive cutoff using data from a known seronegative population. So in that case, you're going to have a very simple case. So you have a sample, of size n, and then you calculate the mean and the standard deviation to estimate the mean and the standard deviation of the seronegative population, and then you plug those estimates in the formula of the cutoff. This is actually what was done in these 2 cutting-edge papers published during the pandemics. So they were they used the 3 sigma rule, and a lot of people actually use this kind of strategy when they did serological analysis of SARS-CoV-2. Of course, I'm as a statistician, and I got a little bit curious about the properties of actually this estimator provided by this strategy. So I thought, is this a good estimator? And so to answer this question, I'm just going to focus on this presentation about the question of the bias of this estimator. So just to remember, the definition of a bias estimator is actually when the expected value of the estimator coincides with the true value of the parameter. So actually, if you do that for the cutoff associated with the 3 sigma rule, you're going to see that it's very easy to do the calculations of the expected values. So you're going to see that you have an unbiased estimator of the population mean, but you don't have an unbiased estimator for the standard deviation of the population using the sample mean and the sample standard deviation. So in a way, what I'm telling you this, just by this formula, I'm just showing you that actually the estimator of the cutoff is actually is biased. So what's the nature of the bias? I'm just bringing here 2 examples. One where you can do exact calculation for the bias, and this is the case of the normal distribution. And then you have for another case, which actually is related to the logistic distribution, when actually you can calculate the bias by simulation. So in both cases, you have negative bias. So it means that this the current estimator of the seropositive cutoff is underestimating the true value of that cutoff. So let me just show you then what's happening in the normal distribution case. So I found out in the literature this paper from the 1950s. So Waltzman actually derived the expression of the expected value of the sample standard deviation, and he showed that actually the bias is actually biased, but the bias can be corrected by a factor that is dependent on the sample size. So actually, if you use this n-Bayer estimator of the standard deviation, and then you can plug it in the formula of the seropositive cutoff, then you're going to have unbiased estimator of the cutoff. But this is just for the normal distribution case. And I emphasize again, this is not used in practice. So what happens when actually you have non-normal distributions? In that case, I found interesting paper from 1971 published in the American Statistician. So Gurland and Tripathi, they derived an approximated unbiased estimator of the standard deviation, and it's very simple to be applicable. And then you can apply this this estimator to obtain a new almost unbiased estimator of the seropositive cutoff. So here is just to show you the bias and the reduction of bias using this inversion of, in the case of the logistic distribution. So as you can see that the corrected estimated it actually reduces the bias dramatically, especially in low sample sizes. So while almost finishing, in that case, I would like to go back to the original question of this talk. So the one-sided 3 sigma rule, is it a beauty or a beast in serology data analysis? So I think, in my case, I think it's a beautiful idea coming from a normal distribution, and with a good theory, and there are other results theoretical results related to the 3 sigma rule. The beauty of this estimator is because it's so simple, then any person can apply it, and it's very important for in communities that actually the statistics is not so developed. So in the case of the beast side, I think I can say that you have a current estimator of the cutoff is actually negatively biased, and this is particularly problematic when you have small samples. And this is actually small samples actually been used in several applications that actually I didn't have time to go through. This rule actually doesn't have so much appeal for non-normal distribution. So you actually can have, especially for skewed distributions, you can have big deviations from the percentile associated with the 3 sigma rule associated with the normal distribution. Of course, you can correct the bias of this the current estimator of the cutoff, but that requires the knowledge of more complex estimators, and I think this becomes more problematic for non-expert audience. So now I would like to finish with the acknowledgements, and I would like to thank the different people who I had the pleasure to discuss this work with, and especially Tiago Domigues, João Malato, André Fonseca from my own research group in Immunostats. I also would like to thank Clara Cordeiro and Giovanni Silva from the Center of Statistics and Application of the University of Lisbon. I also would like to acknowledge 2 people from my department, the Professor Biasek and Dr. Mustafa Kabus, for their insights about this presentation. And thank you all for listening.